I want to welcome you on our rainy Wednesday morning. It's glad to see the sun's coming out. Perfect day to study organic chemistry. I saw a news article that was talking about some sort of chemical that they spray on crops called methamidophos, something I hadn't heard of before. I don't know a lot about agri-science and crop protection. And I wanted to talk about this compound because the structure seems kind of interesting. And the news article came from New Zealand. New Zealand has its own environmental protection agency, just like the United States has its own EPA. And there was just some ruling on an attempt by maybe some farmers group to petition for an extension. The farmers group wanted to extend the ability to use two insecticides. One of them was methamidophos because it was going to be phased out, and that was declined. The EPA said, no, we're going to phase it out on schedule, and after that you can't use it on your crops anymore. And so I wanted to find out more about this methamidophos stuff. If your crops, you might say, oh, I don't want any pesticides on my crops. But if you're trying to raise a family and run your family farm and your crops look like this, what are you going to do? I mean, this is what things are going to, it's not always easy to have the quote unquote organic solution of putting other pests in there to eat the bugs or whatever. What is methamidophos? It's a selective inhibitor of insect acetylcholinesterase. So that's an enzyme that's involved in neuronal transmission, I think the neuromuscular junction, things like that. And the issue is that at very high concentrations, it can affect birds and mammals, including humans. If you get it at high enough concentrations, that's true for pretty much anything. It's true for salt, at a high enough concentration. If you ate, a bucket of table salt, it would kill you. Let's go ahead and take a look at organophosphates. So I put some organophosphate structures here. It's kind of like a guessing game. One of these is methamidophos. And I think two of these are actually crop protection agents, and the others are chemical warfare agents that are used as nerve agents to kill people. So I'm not sure if you can guess which structures are designed to kill people as advanced chemical warfare agents and which ones are things that they spray on crops. They all target the same thing, acetylcholinesterase, but one is selective, or one set is selective for the acetylcholinesterase proteins that they have in bugs, and the others are selective for the ones they have in humans. And I'll go ahead and tell you which ones, because I don't think you can guess. I mean, is it the ones that have the fluorines that are targeting the insects, or is it the ones that have the sulfur atoms that are targeting the insects, or is it the ones that have the nitrogen atoms? How would you look at that and tell? It's not always obvious. So let's go ahead and take a look at the names of these compounds. So this first one right here, this is called sarin. It's a nerve agent. It's used in chemical warfare. It was used in a subway attack by some cult group in Japan to kill people. Soman is a slightly more potent version of sarin gas. It's also a nerve agent. It's designed to kill humans. And so is taboon. This was, I think, one of the earliest nerve agents that was developed for chemical warfare. Maybe around World War II or slightly prior to World War II. The United States, back in those dark days when everybody was trying to develop more advanced agents, ended up adopting the VX agents. Right? These have a sulfur atom and there's no fluorine on there. All of these compounds target acetylcholinesterase, shut down nerve transmission. You can't breathe, you have seizures, you die. And then very recently in Russia, there's been a series of or maybe there's been some discussion about how Russian agents might have been using even more advanced nerve agents to kill people through assassinations. And this is one of those that was discussed, Novichok 5. It's one of the most advanced nerve agents that's supposedly not detectable. These two over here, these are the ones that are used on crops. This is methamidophos and this is diazinon. They're both scheduled to be phased out, and they look awfully similar. Does that mean you're going to die if they spray it on your crop? No, it's the concentration that matters. These are selective, were designed because they are selective towards insect acetylcholinesterases. But I suppose if you took that 5-gallon jug and started chugging it or just took a shower with it, you'd be in trouble. Just don't do that. Yeah, that's so Kind of interesting to note, I mean, and you must have known this already, that the acetylcholinesterases in one organism can have completely different amino acid sequences and binding pockets and activities from acetylcholinesterase in other organisms. Oh, this is so exciting, because when we left off on Monday, we finally started to talk about enolates. We started talking about deprotonating the carbon atoms that are next to carbonyl groups, making carbanions and then using those carbanions as nucleophiles. That's really the meat of this chapter. There's some other stuff in this chapter, but there's this other form called an enolate, and we'll talk about enols, where that carbon that's next to carbonyls can be nucleophilic. And so I want to talk a little more about this naming, because this alpha carbon idea that we've mentioned before, you've heard of that idea before. So when we name carbon atoms to just give a rough, not IUPAC, but just to give people a rough general description, we use these Greek letters, alpha, beta, gamma, delta, to describe how far away we are from the carbonyl. This is true for amino acids in biochemistry, right? Every single amino acid that is encoded ribosomally into proteins is an alpha amino acid. There is an amino group at the alpha position of the carboxylic acid carbonyl. And so we use this nomenclature is common to all of organic chemistry. This carbon atom right here, this carbon atom is called the alpha carbon. And let me just go ahead and highlight these. This is the alpha carbon, this is the beta carbon, this is the gamma carbon. So if I tell you that something is going on with the beta carbon, if I tell you that amino acid is beta branched, you know that's 2 carbon atoms away from the carbonyl. Right? There's also a gamma carbon. Sometimes we have gamma selectivity for some sort of a deprotonation on an enone. And so the farther you walk away, you just keep labeling with letters in the Greek alphabet until you can't remember the Greek letters anymore. Now, one common mistake that I see all the time is when I say alpha proton, what am I talking about? When I use the word alpha proton, I mean a proton attached to the alpha carbon. That right there is the alpha proton. That's the alpha proton. It is attached to an alpha carbon. And the reason I'm making a big point about that is because oftentimes I find that students will misunderstand and think that the H of an aldehyde is the alpha proton. No, you have to have an alpha carbon in order to have an alpha proton. There is no way to deprotonate the H of an aldehyde. That is not acidic in any way. No base that I've ever heard of in my life can pull that proton off. So the alpha proton that is attached to the alpha carbon, that is the focal point for your attention for the rest of this quarter. You have to see the H's that we don't draw and know that we can make carbanions on that alpha carbon simply by deprotonating. So again, with the idea is that we add bases to our reactions. I'll show you that you have to carefully choose your bases, and then we can use those to deprotonate a proton on that alpha carbon. So again, I'm going to draw that proton so I can do an arrow pushing mechanism, but you have to see every single proton, even if it's not drawn for you. Oh, actually, let me push the arrows differently because I can see here, right? If I'm going to make this resonance structure, I have to push the electrons all the way to the carbonyl. So let me go ahead and do that. I'm going to take these electrons, push to the carbonyl, and then kick the electrons up. And that makes the oxygen happy. Oxygen's electronegative. It wants the negative charge. Now, I talked about on Monday that there's 2 different resonance structures we can draw for the enolate. We can draw a resonance structure where we localize the negative charge on the carbon. That's fine. We can draw this resonance structure here where we localize the negative charge on the oxygen. That's also fine. And the book prefers that method because it's consistent with the idea that oxygen is electronegative and likes negative charge. And either way, we can draw arrow pushing mechanisms to show how we form bonds. So if I throw in some sort of an alkylating agent that can do SN2 reactions, I can do SN2 reactions. Now don't get fooled. I realize you've seen reactions where O- can do SN2. That's not the reactive part of this carbon, or of this enolate. The reactive part of the enolate is this carbon over here, the yellow carbon. That's the reactive center. That's what's going to form the bond. And we draw the arrow pushing by starting with the O-, and we push those electrons into the double bond. That's what makes the yellow carbon nucleophilic. It's that donation by O-. That donation is always there. And so if we push the arrows correctly, we'll end up with this. So look at that. I mean, look at this bond here. That is awesome. And I hope you can see we could repeat that. There's still one more H that's sitting here on that carbon. So we could do that again if we wanted to. Make CC bond after CC bond after C. We love this in organic chemistry. We love making carbon-carbon bonds. Am I going to put something like this on the exam? I can't imagine. I don't know. I haven't written the exam yet, but I can't imagine writing an exam where I'm not asking you to make CC bonds using enolates. That's true in every organic chemistry class around the world. They expect you to know this reaction. Something similar to this pattern of chemistry is used in lipid biosynthesis and the synthesis of polyketides, ultimately in the synthesis of terpene molecules, steroids, estrogen, testosterone. Nature uses the heck out of this reaction, and you should too. And this turns out to be a super useful reaction. Okay, we have to be really careful about what kind of base we use to pull that proton off, because we haven't really taught you about the best bases yet. We kind of hinted at it when we told you how to deprotonate alkynes. Your inclination will be to use alkoxide bases, not because you're foolish, but because you've been paying attention for the past 8 months. And the only bases that we really talked about when we said strong base was sodium ethoxide or sodium hydroxide or potassium t-butoxide. And let me show you the problem with all of these alkoxide bases when we want to make enolates. So probably one of the potassium t-butoxide is one of the stronger bases that you've learned about, or one of the strongest bases that you've learned about so far. And let me show you what happens if you try to use an alkoxide base. You know, it doesn't matter whether it's t-butoxide or ethoxide or hydroxide. The problem is that we are trying to deprotonate protons here on the alpha carbon. Those protons have a pKa of about 20. So that's for a ketone. And I'll show you in one of the following pages that I'm going to expect you to know that pKa. I expect you to know the pKa for a ketone like acetone, pKa of 20. That's not as acidic as water. You can't use hydroxide or t-butoxide to efficiently deprotonate that. And I'll show you how you could know that. So when you deprotonate, I'm not going to draw the mechanism, but when you use this alkoxide to pull one of the protons off of here, you make the enolate. But you don't make the enolate in high yield. You only get about a 1% yield of the enolate. It's an equilibration reaction, back and forth, this deprotonation event, if you treat that with t-butoxide. And what's going on is that you also generate at the same time the acid, the conjugate acid, from your base. Now we can use the pKa of that conjugate acid to estimate the equilibrium constant. Let's go ahead and do that. So the pKa for the acid on the starting material is 20. The pKa for the acid in the product side only has, and this is more, this is even less, so I'm being generous here. This is less acidic than water. Water is about 16. Most alcohols are about 16. You don't have to memorize t-butanol. You could use 16 here and come up with the same kinds of conclusions, right? How do I estimate the equilibrium constant? The equilibrium constant you can calculate by saying 18 minus 20. That's how you calculate the equilibrium constant. 10 to the 18 minus 20. That's 100 to 1. That's 0.01. At best, all you can do, if you heat the reaction, no matter what you can do, all you can do is get to this equilibrium 1% faster. You can't change that equilibrium constant. That's determined by the pKa's, and you don't get to adjust the pKa's. The best yield you'll ever get. This is why we don't like to use alkoxide bases to make enolates in organic chemistry. It's not workable. We'll show you a few cases that worked for reasons that they don't tell you, but in general, we have to use a stronger base than an alkoxide base, and I'm going to show you the base that we prefer. It is called lithium diisopropyl amide, and I'm going to make a big deal about this. The abbreviation for that is LDA, lithium diisopropyl amide, and let's watch what happens when we use lithium diisopropyl amide. And it's not just the massively powerful base that we're using here. It's the special conditions that we use. I'm not going to go into details on what makes these conditions special, but you have to write LDA, THF minus 78 every single time you draw this base. Okay, so again, this is the same ketone. The pKa for that ketone is still 20, so let me just go ahead and write that down. That's those alpha protons next to the carbonyl. But let's go ahead and draw out the conjugate acid from our lithium diisopropyl amide. The conjugate acid from there is an amine. And amines, NHs, are not acidic. It's hard to pull that proton off. In fact, you have to use butyllithium is the only thing that will pull that off. And the pKa for amine NHs depends on what the alkyl groups are. For this compound, it's about 35. You know, it doesn't matter if you memorize 32 from another amine, or 33, or 34, or 35. The equilibrium constant for this reaction is something like 35 minus 20, 10 to the 35 minus 20, 10 to the 15. You get the idea? I don't even know what percent. It's like greater than 99.9%. If the equilibrium constant is 10 zillion, does it matter whether it's 100 zillion or 10 zillion? It's a zillion. It favors 100% yield of the enolate. When you want to make enolates, you use LDA in THF at minus 78. Lithium diisopropyl amide. Do not use alkoxide bases. I'll show you a special case where you can use alkoxide bases and efficiently make enolates, and that's not this simple ketone case here. Okay, so we need to talk about what are those special cases where we can efficiently use alkoxide bases. Well, let's go ahead and talk about that, but get used to this. You're just going to think, man, what is it with Van Vranken and his LDA thing? Man, can't he just get off of that? Nope, I'm not going to get off of it. You got to get used to this. This is going to be our power reagent for this chapter and the next chapter, and for the next exam and the final exam, and for all classes in organic chemistry. Okay, I've got to talk about these two classes of carbonyl groups, because one class, you have to use LDA. The other specialized class, you can get away with alkoxide bases. So I'm going to give you two classes of compounds here in this chart, and I expect you to know these pKa values. You have to know them. And there's no shortcut to that. You just have to, and it's really the trends I want you to know. Can't imagine asking you to tell me the specific pKa, but I expect you to know the trends here. Maybe it would help you to memorize the trend if you just memorize the numbers. So all of these just regular carbonyl compounds that I've got over here on the right, they all have pKa's. So notice all of these just have like a single carbonyl group. Let me come back over here and draw the yellow on the carbonyl. A single carbonyl group, a single carbonyl group, a single carbonyl group next to the CH3. And you'll notice I'm grouping together with carbonyls nitriles. They've got, a nitrile has 3 bonds to a heteroatom, 3 bonds to nitrogen. It's kind of like having 3 bonds to oxygen and nitrogen in an amide. So this nitriles can be deprotonated just like carbonyl derivatives on that alpha carbon. And you can see that all of these are less acidic than water. Water has a pKa of 16. Higher pKa means less acidic. All of these are less acidic than water. You cannot use sodium hydroxide to deprotonate these efficiently. You can't use sodium methoxide to deprotonate those efficiently. You cannot use sodium ethoxide to deprotonate those efficiently. You cannot use potassium T-butoxide to deprotonate those efficiently. All of these, over here on the left-hand side, you have to use LDA to deprotonate those. That's what you have to use, because all of those have pKa's higher than an alkoxide alcohol conjugate acid. And you cannot have alcohols in the presence of these enolates, because if you put an alcohol, if you make an enolate from any of these with one carbonyl group, and you have an alcohol present, the alcohol is simply going to protonate the enolate, and it's over. It's game over. So all of these we deprotonate with LDA. All of these we avoid water or alcohol OHs. You can't have those present. And this is the way we do modern organic chemistry. Let me put you into a time machine and take you back 50 years. So 50 years ago, they hadn't invented LDA. LDA came around, was developed around 1970. And so how did people do enolate chemistry before the discovery or the development of LDA? Maybe it was mid-60s. I can't remember. It's so long ago. Who remembers that stuff? But the book is big about this. And there is one reason for them to teach you about it. But let's go ahead and talk about this historical situation more than 50 years ago, where people didn't have massively powerful bases. They only had alkoxide bases. And here's the kinds of carbonyls they would deprotonate. Notice that when you have 2 carbonyls next to the CH, then it becomes very acidic. See, the pK is only 13 when you put 2 carbonyls next to the CH, 2 carbonyls next to the CH, and this isn't really a carbonyl, but you get the idea. 1 carbonyl in a cyano group. when you have two of these carbonyls or nitriles next to the CH2, all of these pKa's are lower than the pK of water. They are all more acidic than water. So pK of water is 16, pK of these is lower. You can use hydroxide to deprotonate those. You can use sodium methoxide to deprotonate those. You can use sodium ethoxide to deprotonate those. Now I'm going to give you some caveats there because you still have to choose very carefully which alkoxide base you use. But all of these are acidic enough to be deprotonated efficiently in good yield by alkoxide bases. And this is what they used to do 50 years ago, is they used to use alkoxide bases because that's all they had. And then they would make compounds they didn't want that had two carbonyl groups and then remove one of the carbonyls through some complex chemistry I'm going to show you. Okay, you can see there's a general trend here. And that general trend is that when you have, when you have lone pairs next door, nucleophilic lone pairs, like on an oxygen or on a nitrogen, it makes it harder to deprotonate. It makes it harder to deprotonate. The more nucleophilic that lone pair is, here versus here, it makes it harder to deprotonate. That's because if you look down here, that lone pair is donating in. That lone pair is donating into the carbonyl. So if you're trying to get your base to deprotonate and donate into the carbonyl, but you've already got a lone pair next door, that lone pair next door makes it harder to pull the proton off. It's like you want to give the electrons when you deprotonate to the carbonyl, but there's already that other annoying lone pair donating in, so lone pairs make it harder to deprotonate. And you can see if you have a CH3 group, a methyl group that has no lone pairs on it, that's the easiest of these to deprotonate. Lower pK means more acidic, means easier to deprotonate. So that's a trend you need to know, or you could just memorize these pKa's. And that's why you see this trend in pKa's, is because of this lone pair donation effect. Makes the esters are harder to deprotonate than ketones, and amides are even harder to deprotonate. And we need LDA for these simple compounds that have a single carbonyl group on there. Okay, so you're going to have to know about these two bases, alkoxide bases like potassium T-butoxide versus amide anion bases like lithium diisopropyl amide. Now, LDA is useful not just because it gives you high yields of enolates. Yes, it gives you 99.99999% of the enolate, and that's what we love. I'm not saying we isolate the enolate. Nobody isolates the enolate. You make the enolate, and then you use it right there before you head home for the day. So we don't isolate and purify enolates. We just make them and use them right there. Now I want to talk about the selectivity. This is really why LDA became powerful, because you already know an amide anion base that is not very useful. Let me just remind you of this amide anion base that you already know. So recall back from chapter 11, you learned about this amide anion base called sodium amide. It's just as basic or about as basic as LDA. So why don't we use sodium amide? Well, I want to talk about why we use LDA. LDA is selective and sodium amide is not. So let's talk about selectivity. This is a big deal here, this selectivity thing for why we use LDA. And I'm going to try to fix 8 months of misthinking by you about selectivity. And there's nothing that you've done wrong. It's that you've been kind of tricked. The book pulls the wool over your eyes thinking that selectivity always goes one way. And let me try to explain that. So you learned about making carbocations back in the first quarter of organic chemistry here at UCI. You learned that if you take alkenes, the alkene will have 2 carbons, and when you protonate those with a strong acid like hydrochloric acid or hydronium ions, you can put the proton on either of these 2 carbons here. Which carbon picks up the proton? And you were given a simple rule to predict which carbon gets the proton and which carbon gets the empty p orbital, the carbocation. We also call that a carbenium ion. And you were told that if you had 2 choices, one of them is to form the primary carbocation, and the other choice is to form the tertiary carbocation. You were told you always form the tertiary carbocation. That is absolutely true. And why do you form the tertiary carbocation? Because it's more stable. It forms fastest and it is more stable. That makes sense. More stable things, you'd expect to form that faster. you were also shown that when you make radicals, when you use reactive halogen radicals to abstract H atoms from alkanes, and you have a choice. You use a choosy radical like Br dot. Chlorine's not very choosy, but Br dot's choosy. And when you abstract, we use a different type of arrow pushing for making radicals. You were told that when you abstract, we use these half arrows, when you abstract H's using Br radicals, that you form the more stable radical, the tertiary radical, the fastest. The tertiary radical is more stable, the tertiary radical is faster, and that picks up a Br from Br2. So you get the tertiary alkyl bromide, which is great. You can make a Grignard reagent once you make an alkyl bromide. Now, you'd think from all this stuff they've been teaching you that the more stable thing always forms faster. That's true half the time in organic chemistry. Half the time, the more stable thing forms faster. You know what? The other half the time, the less stable thing forms faster, and they didn't tell you about that. So you'd be logical in thinking more stable things always form faster, but let's talk about LDA, because it's the opposite. With LDA, on a typical ketone, like this one that I've drawn down here, there's CHs on both sides of this ketone carbonyl. You could pull an H off the left side, you could pull an H off the right side, and so how do you know which one you're going to get when you use LDA as your base? Well, in the case of LDA, there's two different enolates you could form. If you deprotonate over here on the right side, you get the less substituted enolates, the alkene that has fewer substituents. When you deprotonate here on the right side, over here, you get the alkene that has more substituents. And you all already should know, even though you probably forgot, more substituted alkenes are more stable. If you have two compounds that are isomers, same number of C's and H's, the more substituted alkene is the one that is more stable. And we call that the thermodynamic product, the product that is more stable if you can form two different products. But in this case, with LDA, the more stable enolate is not formed in this reaction. LDA gives you the less substituted enolate. It is very choosy. These conditions that you have to memorize, LDA, THF, minus 78 degrees Celsius, minus 78 space degrees Celsius. Those conditions, the less stable product forms faster. And this reaction is irreversible. It is instantaneous. It goes in 100% yield and it never goes backwards and never equilibrates. The thing that forms the fastest is the thing that you get. And we call this the kinetic product. The kinetic product happens to be the less stable product. So you get 100% yield here of the thing that forms the fastest, and it happens to be the less stable of the two enolates. And what you need to remember, most importantly, is that you just get the less substituted enolate when you use LDA. If you have a ketone and you can deprotonate on either side, you deprotonate on the less hindered side, you deprotonate to give the less hindered enolate. So this is not an unusual case. There's lots of reactions that we're not going to show you where less stable products form faster. It was just these carbocation and radical cases where the more stable product formed faster. And I'm sorry to kind of wait till the end of the quarter or the end of the year here to suddenly switch things around on you. It's going to be hard for you to adjust to this idea. But LDA is so powerful and so selective. We love it. Okay, so let's go ahead and go through this situation with alkoxides. What would happen if you did use an alkoxide base? Suppose you just didn't have any diisopropylamine, and you couldn't get any, and you didn't have any butyllithium in the lab to deprotonate it and make your own LDA, which you have to do. So what happens if all you had is sodium alkoxide? So I already told you the problem here, that sodium ethoxide is not a basic enough base to efficiently deprotonate. You only get about 1% of the enolate. So if I tried to make enolates using sodium ethoxide here, I would get this mixture of two different enolates. I would deprotonate on the left side, over on this carbon, and I would deprotonate on the right side. I would get both of these in my reaction mixture. And this is reversible. You'd deprotonate, the ethanol would put the proton back. You wouldn't have very much of this at equilibrium as you're equilibrating between these two sides. You'd end up with this equilibrium mixture. You'd end up with just about a 1% yield of these enolates floating around. But what is semi-interesting, let me make this arrow a little more clear here. The equilibrium favors the starting material. So you've got a lot of ketone, you got a little bit of enolate floating around. But what's interesting about the alkoxide is because it's all equilibrating, is these are equilibrium conditions is you slightly favor, not massively favor, you slightly favor the more substituted enolate. That's the opposite of LDA. So, in theory, if you put in methyl iodide, right, you can get these two enolates to do nucleophilic attack and make bonds here and do SN2 reactions. Those two enolates will do SN2 reactions, and the major product will be substitution of the more substituted enolates. This is the product over here you would get if you used LDA, 100% selectivity. But over here, if you use the alkoxide base, you can get a little bit of selectivity, 3 to 1, maybe, for this major and minor. And the book presents this to you as though it's useful. It's not that useful. 3 to 1 selectivity isn't good enough for us. We need other tricks for this. And the bigger problem that we'll talk about as soon as we hit the other chapter is these enolates that you're forming. Unfortunately, these enolates right here, we'll tell you, those aren't going to just sit around. They're going to come back and attack the carbonyl. So this is why we don't use alkoxide bases when we do enolate chemistry. It's only if you have 2 carbonyl groups that the alkoxides can be useful. So let's just walk through and remind ourselves of what happens when we use LDA in THF at -78, these conditions that I keep referring to. You have to memorize that set of conditions. You can't just write LDA. You can't forget the solvent THF. And you have to know that you only get this good selectivity, great selectivity at -78 degrees Celsius. So let's go ahead and draw the product. There's 2 possible enolates. You get the enolate that is less substituted. The LDA deprotonates on the less substituted side, right? This side over here has an extra substituent. That's more hindered. LDA is so choosy that it deprotonates on the less hindered side. And let me just remind you of the difference between LDA and sodium amide. You notice it's not random here that there's 2 isopropyl groups. Those are sterically hindering. This is the way to think about LDA. Those 2 isopropyl groups are very crowded, and it makes LDA very choosy. That's why we don't use sodium amide. Somebody went through and tried every single alkyl group. 2 methyls, 1 methyl, 1 ethyl, 1 methyl, 1 isopropyl, 1 cyclohexyl, 1 octyl chain. This is the ideal reagent after all that work. 2 isopropyl groups. 2 T-butyl groups, 2 hindered. 2 isopropyl groups, just right. And that's why you need to know LDA. And there's no, so this is why we don't use sodium amide, even though it's just as basic. We use LDA, those 2 isopropyl groups, that's D, lithium diisopropyl amide. And it's an amide anion. Sometimes I draw it with the N-lithium, sometimes I draw it with the N- and lithium cation, but you get the idea. We're not really ready to have a full discussion about alkali metal coordination yet. Okay, LDA, right? LDA, THF, -78. Did I say that enough? No. Let me say it again. LDA, THF, -78. I'm going to keep saying that, and it's going to sink in. It's kind of a lot to pile in here in a short course like this, in a 1/4 course. Now, I want to talk about the structure of this enolate. I told you already that I kind of like to draw this resonance structure of the enolate. You know, do you draw the double bond CC double bond resonance structure, or do you draw the carbanion resonance structure? Let me go ahead and draw out that other resonance structure that we talk about. Right? There's another resonance structure I could draw for this enolate that looks like this. And they both have their advantages. You can use either one for arrow pushing. Let me draw that H right here. You could draw either one of these for arrow push if you wanted to push arrows and show. Either way you draw it, this carbon over here, the alpha carbon, is the reactive carbon. It doesn't matter which resonance structure you use for arrow pushing, you'll get to the right product. They both have their advantages. And when you're first starting off in enolate chemistry, I kind of like to draw it like this, because you can see which carbon is nucleophilic, or which atom is nucleophilic. right? You don't have to guess what the nucleophilic part of that molecule is when you draw this resonance structure. But there is an advantage to drawing it in this other resonance depiction as an alkene, as an enolate, right? An alkene with an 8 O minus on there. And that is because this other resonance structure reminds you that enolates are planar. And you have to know that enolates are planar. That means they have two faces, a top face and a bottom face. And you have to worry, when they act as a nucleophile, does the alkylating agent, the methyl iodide, the ethyl bromide, the tosylate, come from the top face or the bottom face? You can't go into your reaction mixture and force it to just add, grab the molecule and force it to add from one face to the other. The problem is that when you make an enolate, and I'm going to try to draw a planar enolate down below here in this plane. I've drawn this plane, and I'm going to try to draw that enolate sort of three-dimensionally as though it's sitting in this plane. So I'll do my best here to draw it kind of looking like it's that enolate, like it's sticking here in this plane. Here's the double bond of that enolate resonance structure. I'm going to take the case here where there's a methyl group instead of an H on that. And so here's one resonance structure for an enolate. So I can clearly see that there's a top and a bottom face to this enolate. It's planar. You got 6.02 times 10 to the 23rd of these enolates floating around in your solution, waiting for you to add some sort of an electrophile. And I'm going to take the simplest and most boring electrophile I can imagine. That would be, like, what if I had water in there? That would suck. If I had water and it acted as a protonating agent. There's enolates in there. The conditions are basic, so I'm going to use the symbol HB instead of HA. If the conditions were acidic, I'd use the symbol HA. Same idea as HA. So when you protonate this, the enolate can add, right, 10 to the 23rd of these enolates in there. It can, when you have water or an OH or some other species in there that can protonate, the problem is some of the protonation will occur from the top face and some of it will occur from the bottom face. And so if we have this protonation event occurring, right, 50% of your product is going to be protonated from the top face of that planar enolate, and the other 50%, right, top face, and then the other 50% of the protons will add to the bottom face. You'll get a 50-50 mixture. You can't control that. You can't, there's nothing you can do to make one's face of this particular enolate look any better or worse than the other face. Top face and bottom face. I don't want to draw the same color for my arrow pushing. I'll just use a blue. That's not a, well, that's blue. Maybe I should write the word blue, but the bottom line, it's not the, I don't want to have two sets of red arrows here. That would make it incorrect. So when you protonate enolates, this is using sodium methoxide or sodium alkoxide. You're going to generate the alcohol that will reprotonate it back and forth. If you allow enolates to equilibrate, you're going to end up taking whatever stereochemistry you started with. It does not matter what stereochemistry you started with. H on the top, H on the bottom. Once you make an enolate, you've lost all memory of what that initial stereochemistry was. And this process of removing protons to make planar enolates and then having it reprotonate non-selectively from top and bottom, we would refer to that as either epimerization or racemization. How do you know which of those terms to use? Well, in this case, over here, the products have only one stereogenic center. Those two products are mirror images. Actually, one is the starting material, right? There's no difference between these two. As these things equilibrate back and forth, they're mirror images. Those molecules have one stereogenic center. It's inverted, R versus S. So we call this racemization, when you do something to allow two isomers to equilibrate, and you interconvert the two enantiomers. That's called racemization. If I had another stereogenic center somewhere in this molecule, if there was some other stereogenic center over here that wasn't affected by this enolate chemistry, and it stayed the same, then they wouldn't be enantiomers anymore. Then they'd be diastereomers. And so in that case, the more general term epimerization would apply, right? Epimerization could mean they're mirror images, or it could mean we're only inverting one stereogenic center. Epimerization is a more general term to mean, and it is usually applied to the alpha carbon of a carbonyl. That's the most common case for epimerization. Okay, so epimerization is a more general term when they're diastereomers or when these two have an enantiomeric relationship. But those are two terms that you'll hear. Okay, so enolates are planar, and that means when we do SN2 reactions using these kinds of enolates, you have to worry about drawing both enantiomers of the product. You have to worry about the configuration of the new carbon-carbon bond that you form. And be clear to clearly indicate stereochemistry and the presence of stereoisomers, because I ask you to do that on our exams and on our problem sets. Okay, we're going to come back to enolate anions, talk more about that in this chapter, and the entire next chapter is going to be enolate anions, adding to carbonyls. But we're going to take a kind of little detour here to talk about some chemistry that occurs at the alpha carbon that's not exactly enolate anion chemistry, but there's a similar trend. Not quite sure why this belongs here in this section, but it's just seems like it's distracting us. So there's a transformation, a secret recipe I'm going to teach you, where we can take, I actually already showed you that on our first slide, where we can take one of the CHs here and replace one of those CHs with a leaving group, specifically with bromine. That's useful. Once we put a bromine atom on there, we can do SN2 reactions. So let's go ahead and see that secret recipe that we use. It's bromine, Br2, and we need a secret acid catalyst here, which we use as solvent, and that's acetic acid. Inexpensive acetic acid. And that's our recipe. And you can tell that there's a byproduct here that is not interesting, doesn't contain carbon atoms. Who cares? HBr is the byproduct. But that's powerful to put leaving group somewhere. It kind of, hopefully it reminds you a little bit of that free radical reaction, benzylic bromination. Remember back in the aromatic reactions chapter, we taught you how to put bromine atoms on benzylic positions. Mechanism is completely different. This has nothing to do with radicals. And so why would you do this? The reason why you would do this is because, I wish I hadn't drawn that HBr. Geez, if you drew HBr like I did, now there's no room. I'm so excited to do some chemistry with this bromine atom. Now remember, there's two different H's there. You don't control which one is going to react. If I drew the box and said draw the product, I would expect you to do this. Clearly indicate stereochemistry and the presence of stereoisomers, if any. So there's either a wedge or a dash configuration, and you have to indicate that the enantiomer is present. And you can do SN2 reactions on these. So I didn't leave a lot of room. Let me take an example of something that is good at SN2, doesn't have a lot of as much E2, and that's thiolate anions, have less competing E2 elimination. That's supposed to be a sodium cation, counterion. I can barely fit it in there. But you could use that to displace that bromine. And so I'm just reminding you, I'll write plus E here. You know, normally when you do multi-step synthesis, don't worry about stereochemistry. If I draw a product that has no stereochemistry, which is straight lines, you can draw all your intermediates with straight lines. But if I draw a box, and I say draw the product in the box, you have to clearly indicate stereochemistry and the presence of stereoisomers. This is a pretty general process, this idea of doing SN2 reactions. You know, SN2 reactions with S- thiolate anions and amines turn out to be pretty good. We're going to come back to this when we get to our chapter on amines. So if you make this using that acetic acid method, if you take cyclohexanone and you treat it with Br2 and acetic acid, you can put a bromide leaving group on there. And that turns out to be pretty useful. So you got to remove that, because here's where I mean to draw out the mechanism for the reaction. This is the next slide where I'm looking at the, wow, let me just kind of set this aside here. Next slide, all right, because I want to talk about this mechanism and why you get a mixture of these two alkyl bromides. So what's happening in this mechanism here is that the acetic acid, let me draw out the arrow pushing mechanism for this, mech. The mechanism for the reaction, why do we have to use acetic acid as our solvent? The mechanism starts off with an enolization process where we form the enol intermediate. So the mechanism Sorry I drew this there. That belongs on the next slide. The mechanism involves protonation to make this oxonium ion. And we already covered the mechanism for forming enols intermediates. And now we have this A- intermediate that is floating around. I'll draw that. And one of the alpha protons. And that A- could pull the H off the oxonium, but that's not interesting. That'll just go back. The A- can also pull a proton off that alpha proton and generate the enol. And enols are more reactive than alkenes. Enols have that lone pair on oxygen juicing up that CC double bond. That's way more reactive than any alkene you saw back in the alkenes chapter 10. Right? So when that sees a bromine molecule, I don't know if you remember this, but when you did bromination of alkenes, they went through this three-membered ring, cyclic bromonium ion, and then you open up that three-membered ring. The enol just does an SN2 process on this. So the enol just does an SN2. That lone pair on the oxygen makes that alkene nucleophilic. Where is that alkene nucleophilic? It's nucleophilic right there on that carbon. So when the pi bond attacks, let me use red here, when that pi bond attacks that Br and displaces the Br leaving group, we end up getting an alpha addition from either face of that enol. We don't control which face of that enol is more reactive. It's just like the enolate. There's a top face, there's a bottom face, and whoops, I should have drawn the OH bond. Boy, I'm getting really discombobulated here. I apologize, because I know we're going to need to draw this bond in the next step. So we end up adding bromine from either face of this molecule, of this enol intermediate. And so that's going to give us Br on top plus Br on bottom. I normally don't want you to write the stereochemistry when you're doing arrow pushing mechanisms, unless the whole question is asking you about stereochemistry. That's kind of the thing I'm trying to make a point about. So the Br, half the enol molecules add Br from the top face, the other half add Br from the bottom face, so you'll get a mixture. And then the last step of this mechanism is that you deprotonate in order to make your brominated product. So let me go ahead and draw out that last step here. Deprotonate, and that's what generates the final product in this mechanism. So just be careful about that. If I draw a box and I say draw the product in the box, that this is a powerful reaction for adding leaving groups, alpha to the carbonyl. That's kind of the opposite of the way we do chemistry. We usually use that enolate as the alpha carbon as the nucleophile. Now you can also add halogen groups under basic conditions. You can use sodium hydroxide to make the enolate and add Br2, but that gives over-halogenation. It is not a useful transformation, and so it's kind of cool to read section 21.7b. It's all about how you can over-halogenate without control, but that's not useful, so I'm not going to ask you about that. And it's fun to read, but I won't ask you to know that. Okay, when we come back, I'm going to talk more about these reactions of halogenated alpha halocarbonyl compounds. I'll show you another secret reaction you haven't seen yet, and then we'll just keep going on enolates and hopefully get into chapter 22.